Sir, number 4M.
Yes?
It's 1, correct? Yeah, 4M.
The last one?
Yeah.
Go on.
Because I just put it in the chapter.
We're going to continue, I'm afraid. Okay, let's continue now. Can we look up, please? Next now. Guys, are we looking up, please? I want to continue. I see people on their phone. Right. So what we're having a look at next now is the end of this chapter, which is the practical problems. So there isn't any new formulas for this. We're just looking at applying the formulas we have to sort of story problems. So we'll start off with an easy enough example, okay? So let's imagine for a moment, so this is my first example, I'll just make up. We have a chessboard. Well, anyways, you know what a chessboard looks like. How many squares are on a chessboard? 64 squares on a chessboard. You all know what game I'm talking about, don't you? Yeah? You know this game? Yeah? Yeah. So, here's the question. Imagine on the first square you place 1 grain. On the second square you place 2 grains. On the third square you place 4 grains, and then on the next, the 5th square, you place actually we'll do 8 grains. Yeah. So what's happening each time to the number of grains on the square? Multiplied by 2. Yeah. The reason I'm doing this is because it's a story about the person who invented the chessboard, 600 years ago. The king was so happy with the game, he said, "What reward would you like?" And he said, "Oh, no, nothing much. Just put 1 grain on the first square, 2 on the next, 4 on the next, and so forth." And I said, "Oh, okay, no problem." So I want you to calculate for me how many grains in total on the chessboard. I'd like you to calculate this. So firstly, is this arithmetic or geometric? Geometric. Okay, so calculate, please. So it's 1 plus 2 plus 4 plus 8, etc. Yeah. Yeah, because I want the total on the board. Correct. 64 squares, yep. What power on the 10? It's pretty big, isn't it? 2.92. Yeah, let's have a look. So, S64 equals A 1 minus or N over 1 minus or. What's the A? 1, and the or? 2. And the N? 64. So this will be 2 power 64 minus 1. And what did you say that was? If it was a 10? 10 power? 19. Yeah? Roughly 10 power 19. That's a big number. to put that into scale for you, 10 power 19 grains would be the total production of grain worldwide. You know, the wheat and barley and so on.
You say 1 minus 2 is what 4, or 1 minus 2 is equals to 2 is what 4 minus 1.
That's what I said. No, did I say it? I wrote it down.
Yeah, I realize.
Is there a question? What's 1 minus 2? And if you divide the top by minus 1, it's the effect of flipping the signs. Yes? Is this okay? I don't know. Yes? I didn't quite hear the question mark at the end of that sentence. Is it a dot 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 or is it a question mark? Right now it feels like a dot dot dot. Okay, and turn away. No. Yes?
So you mean 2 to the power of 63? Or
No, 2 to the 64.
2 to the 64 minus 1?
Yeah. The 1 is down below. Yeah. Is that okay, guys?
I'm confused how you got from 1 minus 2 to about...
Oh, guys, alright, I'll show you. No, hey, shh, quiet. Because there's going to be other people thinking it. Look! Everybody. So this is 1 minus 264 over minus 1, which is minus 1 times 1 minus 264, which is minus 1 plus 264, which is 264 minus 1. I didn't skip that much. Don't sell yourself short now. You have more potential than you realise.
Where did the minus 2 in the denominator go?
What's 1 minus 2?
Minus 1. Oh yeah.
Right, another question now. Another question. I'll give you one to try. So, let's see. Okay, so we imagine there's a ball here at a height of, we'll say, 1 meter, and what happens is it's dropped. So it's dropped from this height of 1 meter, hits the ground. Let's do a different colour. Hits the ground, bounces back up to a height of half a meter. Then it bounces down and up again to a height of a quarter of a meter. So yeah, it's a geometric progression, very similar to the last one, except instead of multiplying by 2, we're dividing by 2. And it'll keep continuing like this. So it'll just bounce up and down, and then the bounces get really small. Yeah. And the question is, what is the total distance it travelled? Find the total distance travelled. So I'll get you started. No, I won't. Actually, I'll let you think about this. I want to know the total here. So it's 1 meter, then it's half a meter, then it's a quarter of a meter. So I'll let you figure out the A and the or here. Total distance travelled. And the story is, you drop it from a height of 1 meter and off it goes. No. No, hang on. Are you telling me it travelled a negative meter? Is that what you're saying to me? No, look me in the eyes. Is that what you're saying?
Is it 1 over 1 minus 4?
Is part of it, yeah. Yeah. And it's, so you're saying you don't see anything wrong with it travelling a negative meter? Thank you. It's yeah, for sure. Let's have a look. let's have a look at the answer. So, guys, watch carefully, please. No, I need you all watching. Okay, so, what are we calculating here? We're calculating the total. So let's write down some of them, okay? So it's 1 plus, 0.5, okay. I'll just write it as a half. Plus, no, plus a half. Plus a quarter, plus a quarter.
Oh, about that.
Yeah.
Okay.
Yeah. Now you see, you all missed that. Every one of you missed that. Up and down. I said, what's the total distance travelled? So,
How's that geometric?
well, this is the thing. We'll have to manipulate slightly to make it geometric. So, what I'll do, I'll change this into 1 plus 2 times a half plus a quarter plus an eighth.
What? How does that make sense?
No, stop. It makes sense if you focus. Every number here is repeated, isn't it?
Yeah.
Isn't it? You have 2 of them all. So rather than writing each number twice, I'll write each number once and multiply by 2. Because every number is repeated twice. Yeah?
That makes sense, but it's still, I don't get how that's geometric.
This is geometric. Right? What's the A in this geometric?
1 over 2.
And what's the OR?
1 over 2.
1 over 2.
Then 2 plus 1.
So 1 plus 2, a half over 1 minus a half.
How is A 1 plus 2?
This is the first term.
1 plus 2.
Oh, yeah.
Yeah. Guys, it's not that hard. You just need to focus here. The first term's a half there. So there's a half. Alright, so that cancels that. So it's 1 plus 2, isn't it? So the total distance travelled is 3 meters. Yeah. This was an exam question a couple of years ago. I think maybe one student did not make the mistake of forgetting about the up and the down. No.
So you can't do it with the equation.
I did use the equation here.
You did over 1 minus R.
No, I did. I used it right there. Yeah, and added 1. Yeah.
Sorry, Steve.
Yeah.
The formula we use is A over 1 minus R, right?
Yes.
Why do we have the 1 plus 2 in front of the A over 1 minus R?
Oh, that's like the whole. All right. Right. Question. Is this series geometric? Yes or no? No. It's not, because what do you multiply here? A half, and here 1, and here a half, and here 1. It's not geometric. However, each of these are doubled. There's 2 of them. So if I take the 2 out and take the 1 out, I can be left with a geometric.
So if you rearrange the equation,
By rearranging it, yeah.
part of the equation is geometric.
Part of it's geometric, yes.
I understand why the 2 is there, but why is the 1 there?
This one.
Yeah.
Why is it there? Because it initially fell 1 meter. Yeah. Very interesting. Alright, another one now. No, I made it up, but it's kind of like number 9. But it's different numbers. Right, next one. Let's see what one do I do next then. Okay.
How come we didn't do the third type of series here? There's geometric arithmetic and then there's something with
There's a quadratic Fibonacci.
Yeah, Fibonacci.
I know it's not part of the course.
Not part of
Yeah. Okay, can I scroll down? Yeah. Yeah. Okay. So time for that one. Yeah, that one. 15. Okay. So here's another one I want you to try. So one common application and one common problem that you'll have to face with geometric is something like this. Imagine you had some finite resource. It really doesn't matter what it is. Like, it could be oil, it could be trees, it doesn't matter. There's obviously a finite number. Okay, so whatever it is, we'll just imagine it's, we'll just say there's 100 units. Okay, whatever you want, gold, titanium, but whatever, finite amount of that material. So let's imagine people use 1 unit per year. Right, well, how long will this supply last? Well, 100 years. Obviously, there's 100 units and you use 1 unit a year. But of course, this isn't real life, because what will happen is, as people are using more, demand will increase. So perhaps in the first year people wanted 1 unit, but perhaps in the next year they want 1.5 units. So will this mean it'll last 100 years? More or less now?
50 years.
Less. Well, we don't know exactly. We don't know. So let's have a look at an example like this. So we'll keep it easy enough numbers. Okay, there's 100 units, and in the first year there is 1 unit consumed in year 1. So I'll just write years here. Right, so year 1, and consume 1 unit. And in the second year, we'll say it increases by 1%. So that's 1.01 units used. Then in the third year, it increases by 1% again. So that'd be 1.01 squared, whatever that is. So what's happening here is the population is increasing by 1%. So the demand is increasing by 1% each year. That actually forms a geometric sequence here. The supply will not last 100 years because the demand is increasing. I want you to try and work out how long the supply will now last. Roughly, okay? So how long will it last? Arithmetic or geometric? Geometric. Sequence or series? No, series. Because the total consumption is 100. And when we say total, that means we have to add. 1.01 increase per year. So year 4 will be 1.01 cubed is used that year. Think about this for a minute and try and tell me how long until the supply is gone.
The total is 100, yeah?
That's the key to this. The total is 100, yeah. Yeah, kind of like that, yeah.
So you're trying to find when the C becomes 100 from addition? When the sum of all
Yes, correct, yes. From addition, yeah. So this will continue, but it will stop at some n. I'd like to know what the n is. Yeah. How long? Ah, wonderful. So it'll last more than 100 years. Yeah. No, this is a miracle. People are using more and it lasts more than 100 years. Yeah, miracle. It's renewable supply now, yeah. Okay, shall we have a look at this?
Can you wait for a second?
One sec, okay, one sec. Okay, let's have a look now. So if you think about it, the problem boils down to doing this. If you were to add up how much was used, the total should be 100 units. Okay? If you add up how much was used in each year, the total has to be 100, because that's how much you have, 100 units. So basically the problem becomes this. Can you figure out at what point this total will become 100 if you were to add it all up? So the formula for Sn we know. It's n over 2, sorry, wrong formula. A
Over
1 minus Rn over 1 minus R equals 100. Can we figure out the n? Let's try. So what's the A? The A is 1, very good. And what's the R? 1.01. That's to equal 100. Okay, so that's 1 minus 1.01 power n. That's 0.01, isn't it? Oh, thank you. Minus 0.01, yeah? Equals 100. Is that right? Yeah. So that's 1 minus 1.01 n equals minus 1 if I cross multiply. So that means 2 equals 1.01 n. Now here's the small problem. We haven't learned how to figure out what the n is here yet, and we'll do that soon. That's why I said roughly. So we'll use our calculator to try and figure it out. You reckon it's about that, yeah? 1.01. So if I was to say maybe n is 50 years, is that a solution? It's a little bit short, isn't it? So maybe it's 75. That's a little bit too much. So in this way you can figure maybe 69, nearly 70. It's a little bit too much. So yeah, basically if I was to say in what year will this supply run out, it happens somewhere between 69 and the 70th year. Sometime in the middle of this year. So if you were telling someone how long the supply would last, would you tell them it lasts 69 or 70 years? No. You need to listen carefully. If it was your job to... No. Stop talking. Just listen to me. Listen. If it was your job, somebody asked you, how long will this supply last? And you had to give them a number of years. Would you say 69 years the supply will last, or would you say 70 years? Now before you answer, take a few seconds to think if what you're saying makes sense. No, I didn't say that. I said number of years. You need to give the person a number. What would you say? What would you say? 69. You would have to say 69. Suppose that n was 69.99. Would you say it lasts 69 or 70? 69 still. Yes, correct. Very good. You can't say 70. Yeah, because if you say 70, you're telling the person that their supply will last up to 70 years, and they'll discover in the last few months it will run out. So it's better to leave them with a surplus than a deficit if they have to make plans, you know. So in these situations, and by the way, This comes up in the exam, where you have to make a choice on rounding up and rounding down. And they do like to add this in the exam. They do like to trick students a little bit. You know, they make the student get an answer like 6.9, and they have to round it off. And you know, half the class will round it to 7, thinking it goes up, but because of the story, it has to be 6. Because you, for some reason, you can't leave the person short. It's a very common, sneaky 1 mark they put in the exam. You need to be careful with that. Okay? So this supply, instead of lasting 100 years, will now last 69 years. Okay? Yep. Yep. Okay. Another example now. Yeah. One more example before you try some. Okay. Okay. Right, look up. Look up. Thank you. Now, watch. €5. So, imagine this was in my bank account, and this was all that was in my bank account. My bank balance would say, so here's me. I would say, I have €5. Imagine I went to the shop, I paid for something. Where's the €5 now? It's not in my account, it's in someone else's account. There's the €5. So has the total amount of money changed? No. Here's €5. It was in my possession, it's in somebody else's possession. In total, there's still €5 that can be spent in the community. Right? Can I spend this now that I've spent it? No. But someone else can spend it. Alright? So this isn't actually quite right. And this is what the next example comes into. So we'll picture it like this. Here's bank account number 1. So this is my bank account. I go into the bank with my €5 and I put the €5 into the bank, so it's gone. The bank now has my €5. So I don't want to lose this actually, it's very important to me. So it's gone, it's in the bank. So I could use my bank card now up to €5. Okay? But however, the bank lends money out. You know this obviously, the bank lends out money. And it lends out my money. And the way it can do this is because it knows not everybody will want their money back at the same time. So for example, if everybody here was to put €100 in the bank could lend some of that money out. And you might say, well, what happens if I come back looking for my money? Well, that's okay, because as long as you don't all look for it at the same time, the bank will be okay. So imagine you all deposit €100, and then the bank lends €1,000 to somebody. Well, this isn't a problem, as long as not all of you want your €100 back at the same time. Yeah, they don't lend out all the money, they lend out some of the money. Oh, stop talking, listen to me. Each one of you deposits €100. Okay? So the bank has lots of €100. So it decides a poor teacher like me needs a lend of €1,000. So it gives me €1,000. Is that a problem? Only if everybody wants their money back at the same time. But as long as they keep enough money for the demand that people have, then it's fine. Okay, this is how banking works. So if you want to destroy a bank, all you need to do, it's true, is have every customer look for their money back at the same time. Then the bank closes. And there's actually a name for this in English. Not quite defaulting, no. It's a type of default, but it has a name. Does anyone know? No. Bank run. A bank run is when all the customers want their money back at the same time and the bank can't provide. Have you not heard of this one before?
Yeah, back in 2000.
The true, yeah. Why might all their customers want their money back at the same time? Yeah. Do you realise that's the problem? If people think the bank does not have enough money to pay them back, then everybody will want their money back and the bank will not have enough money to pay them back. You see the problem with that? It's a confidence problem, right? It's a confidence problem. Okay, anyway, how much does the bank lend out? So the rule is, believe it or not, the bank only keeps 10% of the money. So if I gave it €5, it will lend out to somebody else €4.50. It'll only keep 50 cents per €5. So, in somebody else's bank account, they now have €4.50 because they got it from the bank. Okay? Now, that person gets the €4.50, that's great. They spend it, they put it in their bank account. What happens to that $4.50 in the other bank? It gets lent out again. The bank keep 10% and lend it out. So in bank account number 3, what's that now? €4.05 is kept. Now you can see what's happening here. This is geometric. What's the A? 5. And the OR? 0.9. So if I was to repeat this process forever, how much money is on deposit? Well, the total money on deposit would be this, which is 5 over 1 minus 0.9, which is €50. My €5 has produced €50 on deposit for spending in the local community. Okay, but there's only a €5 note. Nothing else exists. There's still only my €5 note, but yet €50 can be spent. Okay, so this is the miracle of banking. It can produce money. The government doesn't make money; banks do. That's the point. Okay, if the banks didn't lend out this money, then €50 has left the economy. Okay, so this is an interesting example of geometric infinite sum. Yeah, I think there's a question in there like this one. Now, what I need you to do, unfortunately, I do need you to do all of these. All of these is necessary.
So will you give us 2 days for it?
Yeah,
Select Friday.
but the next lesson is
Give
so
us the
easy.
weekend. Give us the weekend.
Because this is gonna take a while.
No, it won't. When's our next class?
Friday.
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 What is it? 1 or 2 hours? 1 hour.
Definitely.
I tell you what, get a start on these now, and then in Friday's class we'll give that class over as time to finish working on these. Okay? So just get a start on them now. All right, we'll just do them for a few minutes. Yeah. Which number? Number? Oh, which one? We did one like number 9, but different numbers.